Okay, another kind of short one today. This one is inspired by one of Kleppner and Kolenkow's mechanics problems. This is the textbook I used as an undergrad at Berkeley. It's a lot of fun, but kind of an older book. It's problem 314, interesting. And the statement of the problem is, imagine we have two identical uniform spheres, planets, maybe some large spherical planets, that are co-orbiting, so they're both orbiting around their center of mass. And of course, because they're identical, the center of mass is halfway in between them. And let's say both of these spheres are made of platinum. I don't know why. That would be a very interesting geological discovery to find spheres of solid platinum out there, but say that they have this density. And that's all we know. And the question is, what is the minimal orbital period? What is the minimum time for these two to rotate around each other only under the influence of gravity for these two spheres? So this actually doesn't require that much advanced thinking here. Let's start by saying maybe these two are a distance d apart. I'll go ahead and make them both radius r, just so I've got some stuff that hopefully can cancel out. And we know that because these two spheres are interacting only via gravity, that I can basically replace them as 2 point masses that are co-orbiting their center of mass. And since they're identical, they're both going to be moving on circular orbits that have a radius of d over 2. In other words, if I look at the force on just one of them, the net force in sort of this radial direction will simply be the force of gravity, which is going to be, well, g times each mass. Let's call them both m, say. Again, they're identical. Divided by the distance between them squared. Now, the center-to-center distance is actually d, so that is the gravitational force between these. And then I'm going to say, well, that net force on, say, the one on the right is going to cause it to move in a circular orbit. The radius of that orbit will be d over 2, and I can go ahead and use my circular motion arguments to say that this will be the mass of that guy. And then we're going to multiply it by the centripetal acceleration, which is omega squared times the radius of the orbit. The radius of the orbit is just d over 2. Okay, so what do we notice? One of these m's cancels out on either side, and we're trying to solve for omega, or rather, we're going to be relating this to omega. I'll write it as omega squared. And let's see, we'll have a 2, a g, this d will go down here and become a cube, and of course we'll have m. Now we could have just started with Kepler's third law and gotten this kind of immediately, but this is fine. Now what we're going to do is replace this by 2 pi over t, and then let's replace m by the density of this sphere times its volume. And simultaneously notice that the smallest possible d that we could have, which will give us the biggest omega, has to be the one where d is actually equal to r over 2, where they're just barely touching each other. Sorry. What I meant was the smallest possible d would be twice the radius of either one, where they're just barely touching each other. Now doing a little bit of algebra, we can solve for t directly. It'll be a square root. A lot of this stuff cancels, so the 2 cubed here and one of those will cancel down to a 4. The 4 here and here will cancel. There's also a 2 pi here that I'll go ahead and push inside, and we'll end up with 12 pi over g rho. All the r cubes cancel out. Now we can go ahead and actually plug in these values, the given density being that of platinum, and we end up with, what did I get? 51/30 seconds, although that's kind of inconvenient. Instead, let's write that as 1.43 hours. And that's it. That is the minimum possible rotation period that these two platinum things could have. It only depends on their density, which is pretty interesting. And notice that the minimum is about 1.4 hours. You're not going to get two that are cycling around each other at like once per second. That it just doesn't have the density required. QED.